All right, so today we're talking about our next big topic, but we have a few things that we have to discuss. First is that a new homework has been sent out to you just before class, and it's not due for a few days. But the thing is that spring break is in the middle of this assignment, so please don't worry too much about the due date on that. There's only 5 problems. Just get to it when you can. The submissions were great for the last homework assignment, so keep doing that and we won't have any sort of problem. We're going to have an exam coming up. I've decided that I'm just going to do a take-home exam. So I'm going to be sending you a Word file on a specific class day, possibly the Thursday after spring break, and you can just complete it within the Word document. I think that's going to be the easiest way for me to get this done. It'll be a little bit more complicated than an in-class test, but given that we have 24 hours, we'll have 24 hours to complete it. I think that'll be okay. It won't be significantly harder, but I will try to make it to where there'll be enough variation in the answers. So today we're talking about the extension of where we were in our last lecture. So we've got this set of all languages. And we started right here in the beginning with the regular languages. And the set of regular languages, we determined what languages were in there by creating a DFA that accepted it. So if a language like that dot right there would represent even, in order to prove that it was in fact a regular language, we would have to build a DFA that accepts it. The next set of languages that we did, we are now officially done with, and that is the context-free languages. Now, the context-free languages had PDAs, and these push-down automata were able to define what language might be here. So a perfect example would be A to the N, B to the N, which we created push-down automata to accept those. The more that we drew them, the more comfortable we got. Where we would read in an A, we would pop off nothing and push on something as a counter. And then we would also use that same stack that is expressed here with our pop and our push operations. We would do the same thing to sort of check things off. Or we could do a B, pop a hash, and push nothing. As soon as we can build that PDA, we know that the language A to the N, B to the N belongs in the set of context-free languages. Now, we have already seen one language that we are pretty sure is not part of the set of context-free languages. Now, I chose to cut for time the pumping limit for context-free languages, but the language we saw was the language of A to the N, B to the N, C to the N, where where N is greater than or equal to 0. And the problem here is this, that we have to count 3 things. In context-free languages, you can only have one variable. You only have that one stack. So it can be really, really tough to determine whether or not something is context-free or not. But if I would need 2 variables to figure this out, then that's what we would have a problem with. And we kind of showed this, right? Now, your homework assignment includes one that is very particular. It is a specific form of palindrome. It is 2.31, and it's both palindrome and equal A's and B's. Now, here's the thing. Palindrome is context-free. We have built the PDA that accepts it. Equal number of A's and B's is context-free. This is something that we've already built. But the combination of the two right here is not context-free. And I want you to give me an argument on your homework assignment of why that is. And I've made a very specific note. Just don't prove it, just explain it. Why can't we figure that out with one stack? And that's what I want you to figure out for me. But here's the exciting part of today. The exciting part of today is that very briefly, I'm going to talk about our last set of languages. And I do mean that I'm hoping to be very, very brief with this so that we can focus on finishing off chapter 2. The last set of languages we have are called the Turing languages. Just a note here, the Turing languages will eventually be divided into 2 different sets, Turing recognizable and Turing decidable. For right now, we're just going to call this the Turing languages. And for this, we have Turing machines. All right. These Turing machines are extremely, extremely powerful. In fact, they are in every way equivalent to your computer. This means that they are essentially the same as the computers that you're using. This is extremely exciting for me because we now, building machines not dissimilar to a PDA, we can build a Turing machine and determine if a language is recognizable or decidable by a Turing machine. So something like A to the N, B to the N, C to the N, we can build a Turing machine that accepts it so it becomes a Turing language. And what does that mean? It means that there's a computer, that the computer can compute the language A to the N, B to the N, C to the N. All right, so this is a huge, huge, huge advancement in where we're at. And it's only a slight modification to what we saw with the PDA. Now, this stuff was all created, and it's the person that we call the father of computer science. His name is Alan Turing. Now, Alan Turing is so significant inside of our field that I think I've already said this. I actually named my firstborn son after him. He was an incredible personality, and he was, in many ways, the Einstein of computer science. We do call him the father, but he represented such a significant advancement. Because before this, we didn't see a lot of general purpose computing, and if we did, it didn't have the mathematical foundations that Turing theory would provide. Now, I'm going to give a little bit of a tangent here and say that this was an incredibly tragic tale, all right? Alan Turing died at age 41, and he committed suicide. And it's very controversial. If you want to know more about his life, there is a movie written about it starring Benedict Cumberbatch. And I strongly recommend checking it out. I think it's on Netflix, but I might be wrong. It'll tell you more about his life. He was prosecuted for being homosexual and committed suicide at age 41. Einstein died when he was very old, and he continued to contribute to our field for many, many years past the age of 41. Alan Turing was an Olympic athlete. He ran marathons. He was at the peak of his health and the peak of his contribution. So this is really a hard hit for our field that we only got 41 years from essentially the foundations of our field. So anyway, it's definitely a topic that I can go on for some time about, but it's one of the things, unfortunately, that I'm going to have to cut in this era of online classes, is to go in deeply about his life. However, I do strongly recommend watching the movie that was recently produced about his life. All right. So here's the thing. A Turing machine looks like this. Now I know you can't, Dr. Paulo, you know I got that on DVD. I just didn't want to say it. All right, so this is what it looks like. Dr. Paulo, had you seen the movie?
Yes. Yes, I have. Oh, I think it was great.
Awesome.
Tragic, but great.
You know, maybe we can make that part of if it was available free somewhere. Maybe I could do some credits. We should totally make that part of the class.
Yeah, I agree.
Good quarantine material. All right. So this is a Turing machine. Now, for many of you, this looks like a VHS tape or a cassette. Yes, it very much looks like an evil goatee square, right? This is it looks like a reel-to-reel machine, and that's really what these are. These are casings to hold a tape, and the tape has these sections on it. And each section contains a letter. It can be X, it can be 0, it can be 1, or it can be this special character, which is a blank character. All right. But the only thing about it that makes this particularly interesting as a tape is that it is infinitely long in both directions. So it is not constrained. It is an infinitely long tape. Now, the little goatee that I think it was Brandon that said this is absolutely important that there's two sides, because one side is a writer and the other side is a reader. All right. This is what a Turing machine looks like, though. It's this infinitely long tape that we can read and write from. I want to show you what one of these machines will actually look like, first from an architectural perspective. All right, first off, this is where we're going to see a lot of similarity to a PDA. Now, this is actually going to be a PDA. We had a start state, some intermediate states, some final states, and a bunch of transitions in between them, right? This would read in from an input string. And then it would read and write from a very special thing called a stack, right? So we had this, which I guess we probably need to give a name to, all right? So we're going to call this the controller, meaning the state controller, not like MVC controller, right? This is the input string, and this is the stack. This is how close a Turing machine is to our previous set of language, our previous mechanism, okay? The Turing machine has the same set of components. In fact, you could argue that it is simpler than a PDA because while it has these transitions back and forth, it only has one mechanism that it interacts with. And both from the input and output standpoint, there's this infinitely long tape. Now, you might ask, are we still doing the same thing? Yes, we are still checking strings to see if they belong in this language. We are absolutely still doing that. In this case, we start off with our reader pointed at the beginning of our input string. So our input string starts with the string on it. The tape starts with the input string on it, with the reader pointing directly to the first character of the input string. Everything else is this blank character. It's like a bottom half of a square character. And that is how similar the controller and input string are to our previous languages. It's not some drastic difference that we're going to see when we're creating these automata. In fact, we had previously on a PDA, we had from one state to another state a character that we read, a character that we popped, and a character that we pushed. This was read, this was pop, and this was push. A transition for a Turing machine looks like this. From one state to another, we have the character we read from the tape, the character we write to the tape, and the direction, I don't know why I wrote that, and the direction that we go. Oh, I don't know how whiteout works. All right. And the direction that we go, which is right, right or left. Let me try that one more time. Something that we read from the string, something that we write from the string, comma, with a direction that we go, okay? So to label this, we read a character, we write a character, and then we move the reader over either left or right. Now, in previous iterations, and also even in your book for Turing machines, there have been parts that have been optional. For the sake of this, it is a great simplification for you if we simply make each component of a transition required. And let's see what our first Turing machine will look like. And I'm not going to write the Turing machine yet. I'm just going to look at the tape. Now, we're not building it yet, but let's say that we had a string such as A, B, B. Our Turing machine will start with all blanks, left and right, and the reader will start right at the beginning of our string. Now, we know that each time we do something with this, we're going to read a character, write a character, and move the reader. Okay, now you can read and write the same thing. You can do, I mean, it's not ultra restrictive here, but we want to figure out a way to do this. We want to figure out, and here's the thing, we don't have to think about it in terms of a state machine just yet. We can think about it in terms of an algorithm, all right? Think of the tape as like a new version of a data structure, and in a very limited one where we can just read and write from it. And let's think about a way we might be able to do this if we just had a super limited structure. So if this were A to the N, B to the N, which it looks like it's going to be, if we were thinking about how we would check this, I don't need to keep the string A to the N, B. I don't A, B, B. I don't need that to be there. But let's think about it logically. What if I went through and I started my machine, and if an A was there, I clicked an X. I marked it off with an X. Nope, that's not there. We are done. And as soon as I mark an X for that A, I go all the way to the end of the string, and I mark out the last B. And then I go all the way back to our X, and then I mark out this A. And I go all the way back to B. And when I've got all X's, I accept. Let me go through that again, because this is kind of weird. I'm not doing circles and arrows stuff. This doesn't seem like it should be allowed, but let's check it. We go here. Let's do it this way. We read in, and the first thing that we read in is an A. Okay, if it's an A, let's mark it out, and let's go to all the way to the end of the string. And the second we reach the end of the string, let's go back one and match it with a B. And after we match it, let's go all the way back to the left until we see an X. And then when we see an X, we can move to the right one. And if there's an A there, we can mark it off. And we can see if there's a matching B by moving to the right until we get to an X. And then we can move to the left one. And if it's a B, we mark it off. And if that thing to the left is an X, then we can accept that string. I don't expect you to get that. That is like super jumping into the deep end. But let's see what a Turing machine could look like with that. All right. I'm going to write this down, and we're going to follow this, and we're going to see if we can get through it together, okay? We have an initial state, Q sub 0. And there's two things that we can read from this initial state. We're going to start right here. If we're checking for the language A to the N, B to the N, if we read in a B, then we can read a B, write a B, move right, whatever, because we are going to reject the string if it starts with a B, because A to the N, B to the N, no string can start with a B. But when we start, if there's an A, what we can do is we can read an A, then, I'm sorry, I miswrote this. Read a B, write a B, and move right. We read an A, we can write an X and move right. So if we started at Q sub 0 and we read in an A, we can write that as an X and move this reader over to the right. I want you to kind of watch this construction as it happens. And I'm going to be trying to figure this out while I'm talking to you, okay? Now, this is to kick things off. Now I have marked an A, all right? So I'm going to call that this state, marked A. And I'm going to think about what I need to do after I've marked this A. I'm going to find a B that I need to match it against. So I'm going to keep on moving right. Now these are, I'm sorry, there's still a little bit of X there. My eraser is not working very good. Doesn't work as good as a whiteboard for sure. I'm going to move over. If I see an A, I want to go all the way to the end where there's an empty spot, where there's a blank spot. So I'm going to move right. If I see an A, I'm going to write an A and move to the right because I don't want it. If I see a B, I'm going to move to the right and write a B because I don't want it. But when I see a blank, I'm going to move to the left while writing a blank. So I'm not going to change anything. Let's see what this does. We read in an A, we wrote an X, and we moved to the right. That put our reader right here, and we're now at this state, mark A. We're going to read in an A, write an A, and move right. All that does is move the reader over by one. Then we're going to read in a B, write a B, and move right. This eraser is trash. See, this is what happens when you buy Apple products. That is an Apple Pencil, and the eraser doesn't work. All right. So we read in a B, we write a B, and move to the right because that's the next thing that we want to do. and then we see a blank, all right? When we see the blank, we take this transition. We read the blank, write the blank, and move to the left. Now, at this point, I'm going to go from marked A instead of a past tense. I'm going to say this one is present tense, and I'm going to be mark the B. Now, if I read anything but a B, if there's an A there, oh shoot, I'm sorry. If there's an A there, I want to reject. If there's an X there, I want to reject. But if there is, in fact, a B right there, I want to read in that B, write an X, and move to the left. And the state I'm going to bring us to is going to be marked the B. So following this, we moved A, B, B, all the way till we got to this transition where we saw an empty spot, a blank spot on the tape. Then we wrote the blank spot back and we moved to the left. And now we're going to mark the B. When we saw that there was a B there, we wrote X and crossed it out. And we moved our reader to the left. And now, what are we going to try to do? We're going to try to find an A. All right. So we want, from where we're at marked B, we want to skip over all of the B's. We want to skip over all of the A's. Yes, I said all of the A's. All right. Until we find an X. All right. When we find an X, we're going to write the X and move to the right, because look at what we did. We marked this B, and now we're going to move all the way over from our reader. We're going to keep on moving this reader left until we get to an X. When we get to an X, we're going to keep that X there, and we're going to move to the right. And we're going to have an A right there. And what we're going to call this state is mark A. And all we do is if we see an A, we mark that as an X and move right. Now, this complicated little stuffed machine is the beginnings, not perfect, of a Turing machine that accepts A to the N, B to the N. That was a PDA that did the exact same thing, right? These things are not simpler, but why is this important? Why is this much more complex version important? This version is important because it is how a computer actually solves this problem from a mathematical viewpoint, all right? Not a practical viewpoint, but from a mathematical viewpoint, this is how it solves it. Now, here's the thing. I don't expect you to be able to solve these things yet. I wanted you to get a look at them and get a feel for how these algorithms worked, all right? I don't want you writing Turing machines yet. This is a preview. I don't expect you to be there. But I do expect you to think about this. A very simple language, even number of A's. This should reject. What I want you to do is I want you to think about these exact tapes. And I want you to think about using a similar algorithm, how you might solve this with something like a Turing machine. But here's the beauty of it. We don't actually have to write this stuff. We don't. We can write algorithms once we understand the data structure that's being used, this tape. Once we understand that tape that's being used, we can start to build out these Turing machines. All right, so I know that this was crazy. All right, I know it was really, really a big jump from where we were at. What's mostly important is, in fact, this slide, all right, telling us where we're at. I'm very briefly showing you these Turing machines, right? And here's why this is important. These Turing machines determine what is and is not accepted by a Turing, or is not part of the Turing languages. And these Turing machines are equivalent to actual computers, right? And what's most important about this is that now we can start looking and previewing what belongs where that star is. Because that star now represents what cannot be computed, all right? It is a significant question that we're going to get to before you know it. We're going to be answering that question. And the Turing machine is as simple as this, all right? It is as simple as a unique data structure. But if any of you have seen what the Turing bomb looked like, which was the device that was both one of the first general purpose computers, but also was created to break the Enigma machine for the Nazis, which I think everyone's pretty familiar with. It did sort of resemble a lot of series of these tapes, right, where they were able to solve some pretty outstanding problems using a very similar data structure. However, mathematically, it is equivalent. Why is this machine so important? Well, I'm going to tell you something sort of odd. Turing's work wasn't incredibly unique at the time. In fact, Turing's work was extremely derivative of his major professor, who was, or his advising professor, who was Alonzo Church. Alonzo Church did a lot of this work on computability and general computation using a technique called lambda calculus, which is extremely complex and hard to work with and hard to understand. Turing's work was in the creation of these mechanisms that were built on things similar to PDAs and similar to deterministic finite automaton, these well understood mathematical constructs. And by having a similar construct, he was able to create proofs about things that had not existed before, simply because it was no longer in the realm of abstract mathematics, but now it was in the realm of circles and arrows, right? Now, general computability looked like this stuff, right? So it was an incredibly innovative work. And that's really what I wanted to get through today. Get in your head what a Turing machine looked like, why we care, and just to kind of get you pointed in the right direction for where we were going in our final chapter for Computer Science 479. So I'm going to shut up now and ask if there's any questions about things that we covered today.
Is there a particular piece of hardware operates Turing machine from like a I guess it would be a PDA? Is there like a piece of hardware equivalent? Because from the DFA to PDA, we got the idea of a stack in memory, right? Mm-hmm. So it's just the ability to move through like transitions or states.
So instead of thinking of hardware, and by the way, that's a great question. Instead of thinking of hardware equivalent, I want you to think of computational equivalent, which is a little bit different. And I want you to think about it in the terms of the application that they would be for. So DFAs are useful for exactly the thing that's sort of listed in it, and that's state controllers, very simple state controllers. And to be honest, I don't see a whole lot of usefulness of it, except for the expressions that we see, regular expressions. What's the limit of something that's computable by a single line of expression rather than building out a new algorithm to do it? There's no program. And once that starts to click about what a regular expression is really accomplishing, the regular expression is accomplishing a task without engaging code, right? There's no variables. There's no, we're doing it purely on the processor. And that's the computational significance of regularity, is regularity does not require memory. For things like context-free languages, I would say it is in the name of it. The computational significance is that it's context-free. While it might have some shred of memory, it doesn't have the context of anything that happened prior to or after that. It's very, very useful for things like language parsing, but it is not as useful for things like general purpose computing because it's too limited. But our compilers are that limited. That limitation is significant for that computational area, and that's why it's important to have things like PDAs. For Turing languages, there's no real hardware equivalent now other than thinking of it as like a very large tape drive with a computer connected to it. But that's really it. The controller is essentially running the tape drive back and forth, and that's the hard drive or hardware equivalent of it. And it is kind of shocking to think that we haven't gotten any better than that. We have not gotten any better than these circles and arrows and this stuff. It's hard to believe that this is no different than, you know, a major computer that we buy for thousands of dollars. We have not gotten better. We've only gotten faster. So the hardware equivalent is literally the computer that you're watching on right now. I hope that's kind of an okay answer. I know it's a little bit frou-frou, I guess is the correct answer for it, but that is kind of my answer.
Yeah, definitely. That was a good one. I was just wondering how it could possibly draw into maybe like quantum computers, and does that increase computability, or does that have anything to do with computability? Does it
That's a
affect?
great question. This is so general. It's not limited by architecture, such as like things like von Neumann architectures, right? This is not limited by architecture. It's not limited by hardware. It's purely by mechanism, mathematical mechanism. And since it has an equivalence to what all of these other things can do, and in fact, the other things will have more limitations than the general Turing machine, things like computability, this is the maximum of computability. When we create a computability proof using Turing machines, it will fail on a Turing machine, and by extension, we know that there cannot be a computer that can build it. And when I say that, there can't be a computer built that can do it. And when I say there cannot be a computer built that can do it, I even mean things like quantum computing and whatever the hell else kind of computing there is out there that I don't know about. I know that it can't be done because the Turing machine can't do it. It is so generalized that there is no tie to any architecture or implementation, which makes it a particularly exciting mechanism.
Cool.
All right. So, hey, gang, we're going to do lots and lots of practice, and the next couple ones are going to be pre-recorded videos. And I'm going to try to have them all out before spring break, just so if you wanted to catch up on spring break, you definitely can. Lord knows I'm going to be working through spring break trying to catch up with all of this as well. So I very sincerely hope that each one of you is doing well. If you are having any struggles or issues, I definitely hope that you'll reach out to Dr. Paulo or I so that we can help you with any struggles or issues that you're having. Even if it's just being stressed about all moving online, we definitely understand. Dr. Paula and I have been struggling through there with you, but we don't know what it's like to be a student through all this. So seriously, if we can help you out, please let us know, and we'll do whatever we can for you. I'm going to have this posted to YouTube. Try to get working on the homework as soon as you can. Everybody did great on the last homework. I had no complaints about any of the submissions. I'm going to try my best to have those finished graded by the end of the week. have a great Easter. Have a great spring break. Also, if you're close to graduation, please know that we've got a lot of 400 level classes over the summer. We're a little bit lenient with prerequisites. So if you want to get a higher level class out of the way over the summer, we're definitely kind of a little bit more understanding with prerequisites during the summer, especially if you're going to be taking that class in the fall. There is one class being taught. Dr. Paulo is teaching networking and security. It's definitely worth taking. I'm teaching operating systems and database systems, which is theoretical database systems, not the 339. So if y'all looking for a summer course, definitely check out what we have to offer. They're going to be all online this year because we don't have a choice. All right, y'all have a great spring break.